Let's start right off the bat with a staggering, almost unbelievable number, 183,060. That is the exact number of sentences communicated completely independently by a severely paralyzed patient using a brain-computer interface right in their own home. We're talking about nearly 2 million words of fluid, conversational text generated not by hands, not by voice, but directly from the motor cortex of the human brain. Welcome to this explainer. Today, we're unpacking one of the absolute most profound technological shifts of our lifetime. We're going to look at the jaw-dropping medical breakthroughs of neurotechnology that are literally giving voice back to the voiceless. But we also need to take a hard look at the unprecedented threats these very same technologies pose to our cognitive liberty. It's this wild story of incredible engineering, high-stakes corporate races, and ultimately fundamental human rights. Here's our roadmap for today. We'll be moving through the brain-computer revolution, decoding the mind, the race to market, real-world medical miracles, and finally, the ultimate privacy threat. All right, part one, the brain-computer revolution. This is where biology meets high-speed data. Just to ground us and make sure we're on the exact same page, a brain-computer interface, or BCI, is a system that directly translates neural activity into control commands for external devices, completely bypassing physical movement. You're taking electrical signals from neurons and turning them into digital actions, moving a robotic limb, steering a wheelchair, typing on a screen. It's the ultimate bridge between human thought and digital execution. And you guys, the speed at which this field is moving is just staggering. Recently, a company called Paradromics introduced a new benchmarking standard. In their preclinical tests, their fully implantable Connexus BCI hit information transfer rates of over 200 bits per second with a latency of just 56 milliseconds. To put that into perspective, that is 20 times faster than the initial reported performance of other intracortical systems. It's actually faster than the information transfer rate of transcribed human speech. We aren't just slowly spelling out words anymore, we're streaming high-fidelity intent. Which brings us to part two, decoding the mind. How do we actually get from a brainwave to text? So, how do we turn all those chaotic brainwaves into fluid text? Well, it boils down to this three-step pipeline. First, signal acquisition, gathering the raw EEG data. But here's the catch. Neural signals are incredibly noisy and non-stationary. That's where step two is absolutely crucial. A recent comprehensive review showed that 85% of modern studies now rely heavily on artificial intelligence, specifically deep learning algorithms like convolutional neural networks. These AI models are what actually extract genuine meaning from all that noise, which then feeds into step three, the digital output. Without AI, the raw data is practically useless. What's really wild here is how deep that AI integration goes. Because neural signals are so patient-specific and prone to errors, raw decoding alone can spit out pretty high error rates. To fix this, companies are integrating large language models directly into the decoding stack. Neuralink, for example, integrated the generative AI model Grok. It's kind of like the predictive text on your phone, but for your brain. The AI steps in to guess likely words and plausible responses based on the brain's raw output. It just goes to show that BCI performance relies just as heavily on the AI software stack as it does on the physical hardware in the brain. Okay, moving to part three, the race to market. Let's look at the FDA approval space race. We're basically watching three entirely different architectural bets play out right now. On one hand, you have Neuralink using an intracortical approach, literally penetrating threads into brain tissue for maximum resolution. Then you've got Synchron, taking an endovascular route. Their device goes up through the jugular vein like a stent. So no open brain surgery, but you trade off some signal resolution for that safety. And right in the middle is precision neuroscience with a subdural approach, laying a flexible film of over 1,000 electrodes right on the surface of the brain. They're all racing to see which method the FDA will crown as the gold standard. But, of course, it's not all smooth sailing. There's a massive biological hurdle here, specifically what we call the intracortical complication. Penetrating arrays offer incredible single neuron resolution, but the human body naturally fights back against foreign objects. Over months, threads can retract, and glial scarring builds up around the implants. That scar tissue progressively degrades the signal quality. It's a massive engineering challenge to ensure these devices last for decades, not just a few months. Despite those hurdles, we are at part four, real-world medical miracles. This tech is changing lives today. Take a look at this quote published in Nature Medicine. Intracortical BCIs can provide stable, high-performance communication without researcher assistance over extended periods. Honestly, this is a watershed moment. It confirms we're finally moving this tech out of highly controlled laboratories, where you have a team of researchers hovering over you, and directly into the patient's living room. Let's look at what that actually means for a real human being. These metrics are from a clinical trial involving a man with severe paralysis from ALS. Using a BCI at home, he logged over 3,800 hours of independent use over nearly 2 years. He was communicating at 56 words per minute with 92% sentence accuracy, using a vocabulary of over 125,000 words. Think about the independence that restores. Conversing, controlling devices, expressing complex thoughts independently when your physical body simply can't move. It is absolutely a medical miracle. But we have to pivot now to part 5. The ultimate privacy threat, the dark side of the BCI revolution. Here's the terrifying flip side. If we can decode a paralyzed patient's intended speech with 99% accuracy using AI, what happens to the involuntary thoughts we desperately want to keep hidden? Traditional privacy protects external actions, your clicks, search history, location. But neurotechnology introduces mental privacy. We are talking about digitizing involuntary thoughts, emotional states, and subconscious processes, and potentially doing it without your prior or informed consent. As this recent briefing by the Geneva Academy points out, we are walking right into a legal minefield. The report makes it abundantly clear that our current global legal frameworks were simply never designed to protect information extracted directly from the human nervous system. Sure, we have laws for data collection online, but how do you legislate the privacy of a brainwave? So, the crucial takeaway here is this very real list of risks to our cognitive liberty. The Geneva Academy warns of neural data theft. Imagine hackers stealing your biometric brain patterns. They highlight psychological manipulation by bad actors. There's the incredibly dystopian threat of state and corporate surveillance, monitoring your focus or mood at work or school. And finally, extreme cognitive stratification. If only the wealthy can afford these cognitive enhancements, we're looking at deep, unbridgeable divides in society. The Academy is urgently warning us that this is the ultimate dual-use technology. The exact same implant that cures a patient's depression or allows someone with ALS to speak could, in the wrong hands, be used to enforce ideological compliance. Or, on a corporate level, extract your subconscious preferences to aggressively manipulate what you buy. The data is just too rich, and the access is far too direct. So, I'm going to leave you with this final provocative question. How do we protect our cognitive liberty when our very thoughts are online? The boundary of human autonomy is literally being redefined as we speak. The medical miracles we're seeing are undeniably beautiful, but the responsibility to safeguard the human mind is immense. I urge you to critically consider the future of your own mental privacy as this revolution unfolds. Thank you so much for joining me for this explainer.